Do you hear me? Thursday seminar students, do you hear me? Thanks. So at first, since it seems we can't meet in the near future, I will use this Moodle to upload the lecture and give you exercises. By the way, I can also send you the link of this streaming here. All right. Hope that lots of you are there, so let's start it. I think now you can see my mouse also, the pointer. Let's go back for rigid objects. So we can rotate these rigid objects, and if you want to calculate, well, I can enlarge it. Oh no need. Just a minute. Oh, it's better. So this is a rotating object, and if we pick up one point, this P, there is a distance vector from the origin to this P, and the velocity of this point will be the radius, the distance from the origin, times omega, which is the angular velocity. Last lesson we learned about centripetal acceleration and centripetal forces, which is v square over r. If you replace the v with r times omega, you can have the centripetal acceleration is omega square r. That's even true when we don't really accelerate the body. Constant uniform angular velocity motion also means that there is a centripetal acceleration. If we do something to accelerate it, I mean this angular acceleration, to rotate it faster and faster, there will be another component for the acceleration. This is the tangential acceleration. You can calculate it. This is simple how the velocity changes. If you do this claim, and if you suppose the angular acceleration and the r is perpendicular, which is true, in this case, when you rotate something in the plane, that will be r times angular acceleration. So the full acceleration of the point is always the tangential acceleration coming from the angular acceleration and the central acceleration coming from the fact that this body moves on a circular path. The net acceleration is the vectorial sum of these two accelerations. What if I want to calculate the kinetic energy of a rotating system? The simple thing we can do is divide the body into small parts, small infinitesimal small parts, and say its mass is mi and its speed is vi. And since we know the mass and the velocity, it's very easy to calculate the kinetic energy of this small part, and we only have to sum over all these small parts, so integrate all the small infinitesimal small volumes. But if we play a bit with this velocity, we know velocity is the position from the origin times the angular velocity. So just replace the v square with r square times omega square. Of course, for a different point in this body, this r can be different. So r is only true for the body they are on this blue dashed line, which means all these bodies are in the same distance from the axis of the rotation. But if we divide the vi into ri omega square, this term, this mi times ri square, this is the moment of inertia. This is something which is uh, uh, important for a body, rotating body, not only the mass, but also with this ri, it's more or less the shape of the body, the density of the body, and so on. So this is only the kinetic energy of this small infinitesimal small body. If we want to calculate the rotational kinetic energy of the body, we have to sum it for all the infinitesimal small mass of the body. This sum between the 1 over 2 and omega square, this is the moment of inertia. If we want to be precise enough, instead of these small mi bodies, we have to go to the very, very small, so infinitesimal small masses in technical points. That means we will go from capital delta M to dm, the infinitesimal small masses, from delta M to dm. It's not too easy to integrate something by the mass, but we know the mass is nothing else, just the density at that point times the infinitesimal small volume, and this moments of inertia, only rewriting that dm is rho times dv, you can have the moments of inertia as a volume integral over the rho times r square. Rho doesn't have to be constant in this case. It can be anything. So even doing this integral is not easy, but just look at it. So if you want to calculate the moments of inertia for a ring, where the width of the ring is negligible comparing to the r, then this r square dm, since the r will be for every point the same, the radius, this small r can be replaced by capital R. Oh, I forget the square here. And can came out of the integral, since if the position doesn't depend on if the radius doesn't depend on the position where I am on the ring, it can be independent from the integral, it can come out, and the rest is the integral delta m. You can write here 1. So if you integral something, a constant 1, according to dm, that will give you the capital M, the mass of the full body. So the moments of inertia of the free ring is nothing else, just multiplying the m with the square of the radius. With similar calculation, you can calculate the moments of inertia of different bodies. There are some books you can find lots of example. What is the moments of inertia of discourse, of football ball, and so on. These are the simplest ones. So rectangular plate, it depends how you rotate. So according to this axis, or for example, the axis along the longest side. Moments of inertia for a sphere, that's a full ball, and this is a basketball with a thin spherical shell, and moments of inertia of a cylinder. How can we calculate the kinetic energy of a rotating cylinder with the radius 0.2, mass 10, the angular velocity is 10 1 over s, and if the length is 1 meter? So what we learned, the rotational kinetic energy is nothing else, just 1 over 2 moments of inertia of the body and the omega square, the square of the angular velocity. So it will rotate like this. The moments of inertia of the cylinder is 1 over 2 mr square. So let's see, the rotational kinetic energy is 1 over 2 moments of inertia time angular acceleration. Just write the 1 over 2 mr square instead of the capital I. We have all the parameters we need. So 1 over 2 times 1 over 2 is 1 over 4 times 10 times 0.2 square times 10 square. So this is the mass, radius square, omega square. If you do all this calculation, that's 10 joule. So you can see the length of a cylinder is not in the formula of the moments of inertia of the cylinder, and of course it's not in the formula of rotational kinetic energy. So if you rotate a cylinder along its central axis, it doesn't matter how long is the cylinder, it's only the radius and the mass, they are in the formula. Let's calculate for moments of energy of a full ball with the moments of inertia 2 over 5 mr square. So again, the rotational kinetic energy is 1 over 2 moments of inertia times angular velocity square. We write the 2 over 5 mr square instead of capital I, moment of inertia, and if you write the numbers instead of characters, you will get 8 joule. Now please try to solve it with not oh, it's not cylinder, I will correct it, with not a full ball, but also this basketball-like study. So try to solve it and tell me what is the rotational kinetic energy of the body of this thin spherical shell with radius 0.2, mass 10, and omega equal 10, 1 over s. And write the result in the Discord. Thanks. The others, have you managed to solve that? Alright, so first homework is the next page. I will give you different numbers and calculate the rotation kinetic energy for cylinder, this ball-like structure, and this full sphere. So, and also in the Moodle, I gave you an example, a homework, and just solve it till the next week. Now, let's go back a bit. Not for the, yes, but we can start with the work. So work is nothing else, just the path integral of the force. And don't forget the, the naming. If the work done by, for example, gravitation on me means by the gravitational force you had some energy transfer. If it's positive, your energy were increased. If the work done by the gravitational field on you is negative, that means you walked up in the stairs. You for example slowed down, your energy was less. What is the potential? Just a minute. So work is energy transfer. Work done by gravitational force on the body means it will change its energy. This is the potential energy, the work done by the gravitational force. Work done by, for example, this person pushing this box. If there is no friction, it will increase the kinetic energy of the box. If, as you can see here, there is friction, this energy transfer won't create changes in the kinetic energy, but it increasing the internal energy. The internal energy is technically the temperature, the heat. If your work is 100 joule, and if you see like this, the box won't speed up. The box speed will be the same at the beginning of your work and at the end of your work. Then in this case, your work transferred for internal energy. Potential energy, for example, when you lift a book, you did some work, and if your work is positive, you increased the potential energy of that book. If it's negative, you decrease the potential energy of your book. The potential energy can be understood like in gravitational field and, for example, in spring force. There are a few things. So this is so-called mechanical energy conservation. If this is a closed system, an isolated system, and if there is no friction in this system, the sum of the kinetic and potential energy has to be conserved. And this potential energy is not only the gravitational potential energy, it can be a combination of spring force, spring potential, gravitational potential, and kinetic energy. That's true only for situation when there is no friction and when it's a closed system. All right, so here we are. We can calculate what is the kinetic energy. So we can calculate how we increased the not only the kinetic energy, the translational kinetic energy of the system, but also for the rotational kinetic energy of the system. So so next time we will continue with torque, and then we will go for the pure rolling. And if you see my lecture, pure rolling means when the it's not here. Pure rolling means when in this point, I mean, where the body touches the, for example, table, uh, means there is no slipping, means in this case we can talk about static friction. We will go through it again. I just want to remind it before, even before the next seminar. So the pure rolling is technically how the wheels of your bicycle or wheels of your car moves in normal situation. It moves, and the rotation of the wheel and the translation of the car is connected. Technically, the velocity equal omega times r. This is the pure rolling. When you you go with your car on an icy road, you can imagine that the angular velocity rotates like crazy, and the speed of your car, nothing. These are independent. In this case, the contact point between your wheel and the road is not a static point, it's not a static friction, but it's a kinetic friction. With that, we can solve few things, but for that you have to remember what we learned about static friction. So static friction is not a well-known friction, a well-known force at the beginning of the example. We only know its maximum value, and if we solve the example and the static friction will gives you a number which is less than this maximum value, then our assumption was okay. If not, we have to do something else. So it's the same thing we did on the incline. If the static friction was large enough to compensate the parallel component of the gravitational force, the box remained in the same position. If not, it started to slip. Yeah, so we will finish somewhere here. So for next seminar, try to remember what is friction, static friction, kinetic friction, potential energy, kinetic energy. In this lesson, we learn what is rotational kinetic energy, and we will combine all these things. So everything we learned in this seminar, we will use in this pure rolling motion, and I would be very happy when you can solve those examples. Technical question: have you received your result of the test 1? Is there anybody here they want to ask about the test 2 or how to rewrite the test 1? So there are lots of combination. So for example, if you need to rewrite your test 1, and if you can come to the department, let's say till the exam season, you can rewrite it. If you can't, I can create a test in this Moodle system. I don't like it, but perhaps it works. And also, if you can come to the department, you will write a test 2 about this pure rolling. If you can't, you won't write any test 2, but in the exam, I will add you not only theoretical questions, but an example about the pure rolling. If in the worst case you can't come to the department even in the exam season, everything will be online and you will do your exam in the Moodle. In this case, you will have an exam with theoretical questions and examples. In this case, the exam usually not that easy because I can't stop you to use my PDF or use any book. So let's hope you can come to do your exam in the department, because in that case the exam will be as easy as the tests. So the ones they ask me via mail that when can rewrite the test 1, let's wait till December 10, Hungary, the university is closed till December 10th. If they open it, you can come to write the test. If not, you will write it in Moodle. I hope this answered your questions. Any other questions? If not, that please do not forget your homework, upload it till next week, and we will go further with the pure rolling. Bye.